Good afternoon, everyone. So thank you for your attendance to this first workshop related to the design methods for retaining walls. So it will be the first workshop inside this international conference, and the second workshop will be organized tomorrow about the execution technique and their evolution. So it will be shared by Serge Borel from Sélecteur-Jbassi. So as I have to chair this workshop, I can briefly introduce myself. So Sébastien Burlon, Technical Manager in Terrasol, so a geotechnical consulting company inside CETEC. So the objective of this workshop is in fact to present the calculation methods along these three last centuries, so from the beginning of the 18th centuries to now, with four main presentations, and the idea is to only, of course, highlight some specific issues regarding the calculation method about the retaining walls with these four main presentations. So the first presentation will be given by Jean-David Vernhes from Uni-La-Salle, and the objective is to come back on the calculation methods before Coulomb, and especially the calculation methods developed by the military engineers such as Vauban and Bellilor. The second presentation, so I will give this presentation, so will be about the calculation method, this one after Coulomb, and especially by focusing on the contributions from Boussinesq and Cacot. The third presentation by Cécile Morel from CEREMA and by Gilbert Ayoun, who is not available today, so will be about an overview of 50 years of wall construction in France, with the objective to focus on the development of with the objective to focus on the industrial development of gravity walls in France, especially for the construction of the highway network. And finally, the last presentation, so from Emmanuel Bourgeois from the University Gustave Eiffel, will be about the evolution of the finite element method for the design of retaining wall during the last 20 years and its potential evolution. So in order to respect the time schedule, so we can directly invite the first speaker, so Jean-David.
So thank you, Sébastien, and good afternoon, everybody. So my presentation will rather be a history of science than science, as you will see. So to start off with, here is a view of one of those many fortresses that the engineer Vauban had built in the last third of the 18th century. And if you have a careful look on this photograph, you see that those fortresses included some retaining walls built against what they called freshly turned earth, in other words, fill or low cohesion grounds. So those retaining walls were quite vulnerable, and this obliged Vauban to decide to give to all the military engineer community of his time a table to build those retaining walls with dimensions that would be controlled. So given the height of the retaining wall, this table would fix its average width. So this table was based on experience, and this actually launched almost 100 years scientific activity within the French military engineers community, mainly military engineers. So this is a timeline that I built thanks to a document, a very important document that was published in 1808 by Méniel. And this was a report that showed all the work that had been done before him. His intention was to highlight Coulomb's work and to say that it was definitely the best of all those. And as you see, finally, Coulomb is just one of those many engineers that worked at the time. It wasn't the first, of course, he wasn't even the last one in this period. So to work out all those theories, I used some tables, so of course we won't get there into details, but my idea was to try to find common criteria to all these theories to analyze how scientific activities progressed gradually throughout the 18th century. So what we see there first is that there is the first one of them all, Bullé in 1691, who was a real key engineer for all this period, because his theories had a very heavy influence on all those who came after him. So we'll, for a start, have a look at his own theory. So this is what we could call a design model. I had to use two different words to talk about their model. So this is the first type of model, which is a design model. It's very basic, as you see. It just consists in finding the equilibrium between the weight of the wall, so its surface here, and the weight of a certain region of the ground, which looks like a wedge, and he equates the two values and define the unknown, which is x, the width of the wall. But as you see there, so he finds a value, a slenderness ratio value, so h over x, of almost 3. This value ranged into those Vauban had found or decided to impose to all the military community, which ranged from 2 to 5. Then there is a sort of factor that appears in his work, which is 1 over the square root of 2. And this factor came from another model, which I would call an elementary model, that was based on quite a well-known theory of that time, at the end of the 17th century, which is a very simple one for us today, the inclined plane theory, that says in modern words that if you want to stop a ball on an inclined plane, the intensity of the force you use, if the force is in the direction of the slope, will be the sine of the slope angle compared to the weight of the ball, of course. So if the slope is 45 degrees, then you find the coefficient I've just mentioned. Anyway, what we see there, and this is a very early fact, is that contrary to what Vauban had imposed as a standard for building retaining walls, Bullé shows here, or seems to be showing, that x, the width of the wall, has to be proportional to h. So the slenderness ratio should be constant. Let's go a bit further in how Bullé thought the problem at the time. So, as we said, the problem is really dedicated to freshly turned earth against walls. This is very important. For that type of soil, they knew at the time that you can have mounds of them characterized by a natural slope and an angle of repose. So then it's backward reasoning, introducing the solid wedge principle, was to say that as long as you have a mound with a stable angle of repose and considering the wall on the other side, you will consider a wedge of ground between this naturally stable part of the ground and the wall. And as long as you consider, and this is a very important hypothesis, you consider this wedge of earth as solid, then this wedge, if it's unstable, has to slide on the slope, and so it will slide downwards and forward too at the same time. So there is this idea of movement, and this is why the thrust on the wall is due to the sliding wedge. And this is what we have found just before with the two models Bullé has used. So the solid wedge principle is a very long-lasting one, because even Coulomb used it 100 years later, roughly. Whereas another principle Bullé has used was soon outdated, and this is the way he had built up his design model, because he used the idea of adjusting forces, so in fact only the weights of the wall. And if you consider, for example, that the wall is based on a ground with a 45 degrees friction angle, it's equivalent to consider the vertical force, which is the weight, or a horizontal reaction. It's just balancing those forces. But many engineers, after Bullé and three others, and starting with Couplet and Bélidor in the 1720s, considered that the main failure mechanism for a wall was not sliding, but overturning or falling over its downstream toe. So this is why most of the theories, and Coulomb's one is like that, had to find a lever arm somewhere to go, well, to conclude with this, unknown, which is X. So then, to continue analyzing the theories, the 18 theories as a whole, I've found mainly 5 parameters that can help to describe them as a whole again. So the solid wedge surface, the relative densities, converting wedge weight to wedge thrust, Earth's internal resistance, if any, and thrust loading point. So we'll start with the first parameter. If I didn't give numbers but letters, it's because I wanted to say that there's no specific order. In fact, there is an order here, of course, but there's no specific one. So the solid wedge surface shows, in fact, what is the weight of the solid wedge. And this surface is controlled by the natural slope angle that they would have decided. And what we see here is that the 45 degrees slope is dominant throughout the whole century. Even Coulomb used it, in fact, for his numerical application. And even though sometimes they leave it up to the, reader. I want to go backwards. Okay. Whenever they want to use a value for the numerical applications, it's always the same one. It's 45 degrees. What is quite surprising for us today is that, as you see, this is a really highly non-conservative value if it has to stand for most soils in most situations. Then the second parameter to analyze all these theories is the question of relative densities. Of course, normally the density of the wall should be higher than the density of the ground. But as you see there, the Bullies one, for example, it didn't have any factor between the densities of the two solids. There is this 3/2 ratio, which was quite popular after Buchot in 1716 and that Bélidor used. But most authors leave it up to the reader. When Coulomb himself had to use a relative density, he decided for his numerical application to equate the densities of the wall and the solid wedge, what means that this was, on the contrary, rather conservative. Third parameter is a bit more difficult to describe. In fact, it's the idea that if you have a vertical force, which is the weight of the wedge, of course, you need to explain how it comes to push the wall forward or downwards. So the main idea in those times was very geometrical. They were based, first of all, on elementary models. So we've seen what Bullies had used. This was the inclined plane theory. And those who used the inclined plane theory used a force that was going down the slope, and some authors just left it as it is, or projected the force again horizontally. So in the first case, you have, as I said, the sine of the slope angle. In the second case, with the second projection, you have this time a cosine of the slope angle. So maybe you have a multiplication of the two factors. A very different approach is the one introduced in 729 by Bélidor, who decided to consider a ball again on an inclined plane, which would be stopped not by an inclined force, but by a horizontal force directly. And this is the same approach as Coulomb in 1773, because he used an horizontal force and no other direction. So in that case, the factor is the tangent of the slope angle, and if you have a 45 degrees slope angle, then you find a factor 1. So this causes a problem for Bélidor because, of course, he has to explain how some soil doesn't push as much as a liquid of the same density. So if you don't use geometrical projections, then how do you do? So we arrive here at the fourth parameter, which is the question of the internal resistance, if any. So those who have those geometrical considerations, then they don't need this internal resistance. Whereas Bélidor has to use another factor. In this case, it's 1/2. And it looks like sort of K0. Considering all this, Coulomb is totally original there because his approach is interface resistance and not internal resistance with his C and phi theory. Then to finish off with those main 5 parameters to analyze the theories, there is the question of the thrust loading point leading to the lever arm estimation. This needs a foreword. All the elementary, because of Earth homogeneity, the elementary model properties can be concentrated on the center of gravity of the wedge. So having said so, if we consider what the authors made, well, all those who had defined a horizontal force, a thrust on the wall, of course, were bound to find a 2/3 of the height lever arm. Those, on the contrary, who used an inclined force found a 1/3 of the height of the wall lever arm. But none of them could be right because if you consider that I've been talking about solids from the beginning, the only pressure that can be between two solids is uniform pressure. So the net force that you can derive from this situation is bound to be in the middle of the two solids, so in that case, the middle of the wall. So there were only 2 of those theoreticians that found interesting and quite original solutions. Bélidor, because he was the only one to have done that, he sliced the solid wedge into many inclined prisms, each one of them exerting its own force on the wall. So when he made the sort of overall effect of those the slices of wedges on the wall, he found a 1/3 of this is probably the correct solution for cohesionless ground. He found it to be 1/3 of the wall height. Whereas Coulomb, we all know that, of course, minimi and maximi, what is behind this is just using derivatives. So after having found the optimum force through the derivation according the angle, he used a second derivative according to the height of the base of his wedge. And then he integrated all this along the entire wall. But what is very strange in the case of Coulomb is that he decided to put the unity, the force at the bottom of the moving wedge, I say, what as a result concluded as for the overall lever arm to be 2/3 high up the wall, which is not correct if you consider that the way the ground pushes on the wall is a sort of hydrostatic type, again, when you have cohesionless soils. So that makes Bélidor's model a very interesting one for the entire 18th century. Before concluding, we could have a look at a very practical aspect of the problem, which is the resulting slenderness ratios obtained with all those theories. So this was an awkward job because many of the expressions of all those scientists were quite hard to handle, and none of them always entirely defined the slenderness ratios. So I had to fix a certain number of values, trying to keep them as steady as possible among all theories. So what we can see here, according to Méniel, all of those scientists, all of those theoreticians would refer to Vauban. And it's not surprising that, after all, the main values, they're all very scattered, but they usually are in between the 2 to 5 slenderness ratio that was imposed by Vauban's table. There is another aspect here that we can see, is that you have 5 parameters behind, at least 5 parameters behind all these theories, and every parameter is quite hard to determine. There is uncertainty. Also, they have to stand for all the soils, knowing all the variety of the soils in general. So you see that it was very difficult at the time to use Vauban's result to ascertain that one of these theories was the right one. So it was only a rational analysis of those theories that could make that one of them would be the best of them all. But for sure, they all tried to calibrate their theories on Vauban's results, and absolutely not at this time anyway on laboratory testing or anything else. So my conclusion is here that I would like to emphasize that Coulomb's method approach is a very, very long-lasting theory if you take it as an elementary model and not as a design model. Because as a design model, it may be discussed for some reasons I've tried to explain. There is another theoretical problem with Coulomb's approach, and somebody like Coulomb in 1846 had wrote about this problem, is that when you use a solid wedge, you may mix up cause and consequence of the fact that the wall will be falling. Is the slide plane a cause or a consequence of the movement of the sudden movement of the wall? Of course, I'm talking here about equilibrium states, and we're not talking about any strain or anything like that. The second part of the conclusion, of course, is like in 2016 when we, with my colleague Bassam Barakat here, wrote about Bélidor. It happens that after this quite long study on all those authors, Bélidor still stands out today as a very, very interesting theoretician for that time. Because in fact, he, rather than just staying with this idea of an earth thrust, he really had a theory which introduced the notion of earth pressure, which is our problem today. And this earth pressure was proportional to depth, which is correct for cohesionless soils. And his work can be related to Rankin's 1862 earth pressure coefficient approach. Thank you very much.